Hello, I am Ali Bahri from ETS Montreal, where I'm part of the Livia Lab and the International Laboratory on Learning Systems, or ILLS. Today I'm presenting our CVPR 2025 paper titled Spectraling for Mamba for Robust Point Cloud Processing. In this work, we proposed three spectral strategies that adapt the Mamba architecture to handle 3D point cloud data effectively for both supervised and self-supervised tasks. Mamba is a recent state space model that has shown strong performance with much lower complexity compared to the transformers. However, it's not designed for 3D point clouds, which are unordered, sparse, and have no inherent sequence. Our goal in this work is to make Mamba effective on point cloud data in both supervised and self-supervised settings while preserving its efficiency. Now let's look at the core challenges. Prior Mamba-based methods apply 3D grid-based traversal, which is not surface-aware. This causes nearby patches on the grid to be spatially disconnected on the object. Also, Mamba doesn't use self-attention, so it's highly sensitive to token order. Finally, conventional MAE-style pre-training fails in Mamba because inserting masked tokens at the end of tokens disrupts positional continuity, which Mamba depends on forced sequence processing. To address these challenges, we propose three strategies. First, SAS, or surface-aware spectral traversing, defines robust token ordering based on Laplacian eigenvectors of a patch graph. Second, HLT, or hierarchical local traversing, recursively partitions the spectrum for fine-grained segmentations. And third, TAR, or token alignment restoration, reinsert masked tokens into their original positions during MAE pre-training, preserving the token structure that Mamba relies on. Our first strategy is SAS, which defines a surface-aware token traversal using a spectral graph analysis. We start by constructing a patch connectivity graph using farthest point sampling and k-nearest neighbors. Then we compute the first few non-constant Laplacian eigenvectors. This acts as smooth functions over the surface. Using these eigenvectors, we define a patch order for both forward and reverse traversal. As shown in the figure, this spectral ordering is invariant to isometric transformation and captures the manifold geometry more effectively than grid-based traversals. Our second strategy is HLT, which is designed for segmentation tasks. Instead of handling eigenvectors independently like in SAS, HLT recursively partitions tokens using all spectral coordinates together. This builds a binary tree over the spectrum, creating up to 2 power 4 distinct segments. In the top figure, you can see how each eigenvector splits the space and how these splits combine to form the final traversals. This joint spectral partitioning allows Mamba to better capture local part structures. Our third contribution is TAR, or token alignment restoration, which is used in MAE-based self-supervised learning. In a standard MAE, learnable tokens for masked patches are typically appended at the end of the sequences. This breaks spatial locality, which Mamba relies on. As shown in the figure, we instead restore masked tokens to their original positions before reconstruction. This position-aware masking preserves the token order and enables effective reconstruction through Mamba. We evaluate our method on classification, few-shot, and segmentation tasks across data sets like ScanObjectNN, ModelNet40, and ShapeNet-Part. Our approach consistently achieves state-of-the-art accuracy with fewer parameters, and HLT improves segmentation performance in both training from scratch and pre-trained settings. Table. On a ScanObjectNN dataset and ModelNet40 dataset, our method outperforms both point Mamba and PCM. Also, as shown in the tables, in few-shot classification and segmentation, our method achieves good results compared to the point Mamba. As the ablation study images show, using 4 smallest eigenvectors yields the best accuracy, and applying TAR during pre-training consistently improves performance of downstream tests across all datasets. To summarize, we propose 3 spectral strategies that make Mamba effective for point cloud processing of the results across classification, segmentation, and few-shot learning. Thank you for your attention. You can find the paper and code using the QR codes, and feel free to reach out via email if you have any questions.